First, I'll just introduce myself. My name is Francis Cleveland. I work for Xanthus Consulting. I am the convener of the IEC TC57 Working Group 15, which is the cybersecurity for electric power systems. So probably some of my focus is going to be on that, but I recognize that there are plenty of other cyber physical systems than just power systems. So let's get started. I'm going to start with just some definitions. First of all, if you're going to have OT, which is operational technology, as opposed to IT, information technology, it's a little funny separation of the words, but what we're talking about is cybersecurity for cyber physical systems. So cyber physical systems can be seen as smart systems that include engineering, that are interacting with networks of physical and computational components. It's not just computers, they're connected to real-world devices, and these real-world devices have impacts on the physical world. And the need to interact with these physical components from a time sensitivity, from an accuracy, all of that is extremely important. We recognize that not only is there computation, which is the computer side, but we need absolutely communications to all of these physical systems, as well as controls. So this makes cyber physical systems quite different from just plain computers, which IT typically deals with. So as I said, I come mostly from the power system background. So just a short little thing here, a power system is a physical system, but it has overlaid on it an information infrastructure, which is a cyber system. And it's this combination that makes life difficult. In the past, the physical system, humans did everything. Now with the combination, with the addition of the cyber, an awful lot of the work is done by cyber systems. So I would also like to start with some of the key cybersecurity concepts. This is based on a paper that the IEC System Committee Smart Energy has developed. And it covers a lot of information, but what I'm going to cover here is sort of the 5 cybersecurity concepts. It's called for smart energy because this was the Smart Energy System Committee, but the same concepts are absolutely true for any other cyber physical system. So there are 5 key concepts. The first one is resilience. The idea is that it's not just security, but it's resilience. Resilience should be the overall strategy for ensuring business continuity. So it doesn't matter if something gets broken, which it will, whether it's a cyber attack or a failure, a storm, or a fire or whatever. There has to be a mechanism for recovering, coping with a situation when it occurs, knowing that it has occurred, and then working through it, responding to it, and after the incident has been resolved, to come back and start again, maybe fix things, maybe change your cyber response and your engineering response. The two go together. Remember, for cyber physical systems, engineering is equally important to the cyber side of things. Then security, concept number 2 is security by design. I won't get into that here because that's definitely a good approach, but not our topic today. Topic number 3 is concept number 3 is IT and OT are similar but different. And I will also get into that in a lot more detail. But I just want to mention concept 4, which is risk assessment, really critical. You can't solve or prevent all problems. You have to take a risk assessment approach to it and figure out what is the most important and deal with it. And then concept number 5 is that there's cybersecurity standards and best practices. They exist. Maybe they're not complete. Maybe there are gaps in them, but these should be the security standards that are used as a basis for any cybersecurity work. This is really important, and the IEC is in the forefront with these cybersecurity standards. So just again, looking at IT versus OT, we'll get into a little bit more later on, but I think the one thing that I want to point out here is that typically, not 100%, typically IT focuses on preventing access to sensitive data. In the OT environment, it's mostly availability and integrity of the data, because you're trying to have safe and reliable operations rather than sensitive and private information protection. So that's one of the key differences. So what I'm going to do is at this point go through some of the questions that were raised, and I will take sort of a stab at each one of this sort of group of questions. And then after each one of these groups, I will sort of open the floor for questions to see who has some additional types of questions and discussions. I'm not the be all and end all of answers, so I'm hoping for discussions amongst you all to discuss some of the issues. It's not like I am the only expert and I'm only one of many, many, many experts in this area. So I'm going to start with OT and IT concepts. And this is with response to a question that says, with respect to which aspects do you regard IT and OT security as familiar, closely related? And then the second is the opposite, with respect to which aspects do you regard IT and OT security as far apart? I'll get to these other questions later, so let's start just with this one. OT and IT concepts. As I mentioned, IT characteristics, a focus is on confidentiality and privacy. Human interactions with computer systems are the main drivers for security. So it's really that human interactions. Timing requirements are on a, quote, human scale, multiple seconds, minutes, hours. Cybersecurity technologies must reflect people issues using the public internet or private internets. But typically, they may be private in one sense, but they're not really. They're public systems. Another sort of main idea is that computers, since IT is not linked to any physical equipment, that's the concept here. computers can be turned off or applications stopped or deleted if problems arise. That's a key issue. The other thing is that the main impacts of a cyber breach are financial, reputational loss, obviously privacy problems, things like that. Whereas OT, the focus is on availability and data integrity. And the key here is that automation between computer systems is the main driver. Human interactions are usually constrained by well-tested applications within protected environments. And this stems from the fact that engineering has been such an important part of cyber physical systems. You've had to engineer these systems for safety, reliability. These systems don't change very often, unlike cell phones or even computers in the IT environment. These are ones that run, the systems run for years sometimes. The timing requirements can be milliseconds to seconds. So really often very, very stringent timing requirements. And the cybersecurity technologies must reflect automation issues for retrieving, validating, sending data in a timely manner, not usually using the public internet, although that may change with distributed energy resources. This is one of the new areas that's going to be a real challenge for cybersecurity. And computers cannot be turned off if problems arise. This is just, you have to have them continue to operate in some form or another. So engineering is really, really important. This is absolutely one of the key elements. It's a combination of IT and engineering practices. And then the main impacts of a cyber breach are physical. Yes, there could be some loss of privacy or sensitive data, but most of the impact, the serious impacts, are safety related: loss of power, loss of industrial process, loss of medical procedures. Again, just covering a lot of this. So cryptography can be used by both IT and OT systems, and such as PKI, and both data at rest and data in transit need to be protected. Role-based access control is critical for both human and system access management. So cryptography is still quite valid for both worlds. It's the devil's that's in the details. And some of that is because authentication between systems requires different cryptographic processes than human-initiated authentication. There are problems that devices are not always available to reach back to their certificate authorities, unlike most IT environments. So they can't get to their revocation lists, and may use something like OCSP. Lots of end devices need to be treated as a group with group keys. Again, quite different from the IT world. Low time latency may require simpler cryptography. I don't mean from an algorithmic perspective, but simply not as much computational requirements. Authentication, for instance, but not confidentiality. And I think engineering plays a much larger role because of the physical devices. And the break the glass scenario is something that really can be quite important, because sometimes, the physical aspects of the system need you to be able to bypass some security measures, not everything, during emergencies. So one of the things I have definitely found is that the best solution is to make a team of both IT and OT experts and make sure they listen to each other.